Okay, well, thank you very much, Nima. And it's a pleasure to be here and to be lecturing here. And as Nima said, today we will discuss, well, if the chalks don't conspire, the S matrix of n equals 4 superjumbles and of n equals 8 supergravity. Okay, so let me start by giving some motivation. So I can say that at least my interest in the subject, of course, computing S matrix elements in QCD or in any theory has been something that has been going around for many, many years, and many people have developed many techniques, and this is very useful for the LHC and for any particle physics experiment. But at least my interest in the subject started in 2003 with the work of Witten, when he gave a quite remarkable and surprising new way of thinking about the scattering amplitudes. He basically realized that if you think about wall sheet, where you have the most basic kind of interactions on the wall sheet with current correlators, okay? You put n of them there. Now you take this into a space that many of you might be familiar with, which is called twistor space. The one introduced by Penrose in the 60s, okay? Using a map of degree D, okay? This is just a motivation. So that goes into some object in twistor space. And if you furthermore take this object back into space-time, the surprise is that you find the scattering amplitude, okay? So just from a very, very simple interaction here, all the complication of the scattering amplitudes that you see here are just coming from two maps, one into twistor space and the other when you go back from twistor space to space-time, okay? So this very simple picture gave rise to many, many different ways of thinking about scattering amplitudes. But I think I can summarize what we have learned as follows. That the main insight is the following. So if you take Feynman diagrams, which you learned in your first course in quantum field theory, okay, we can compute any scattering amplitude we like. And Feynman diagrams make locality manifest, meaning that we start with a Lagrangian, which is local, which only has local interactions. Feynman diagrams make this locality manifest, but there is a price to pay, and the price is a huge amount of redundancy, which leads to complications and almost impossible to compute in many, many cases, okay? Even with powerful computers nowadays, many scattering amplitudes that you would like to compute are impossible to compute, okay? So this is nice because it makes evolution through space-time manifest, okay? Well, we could ask if this is nice or not. Well, what we have learned from the things that have been developed since 2003 is that all the new techniques, one of them I'll talk about today, build the scattering amplitudes out of very, very strange objects, okay? It's like putting together imagine that you want to make a human being, and you put together lots of aliens together, and finally you get a human being out of it. That's basically what happens here. You build the scattering amplitude out of non-local objects. Okay? This by itself would not be surprising if nothing special happens. But what happens is that if you pay the price of not having manifest locality, you find a remarkable simplicity. And in some cases, like in n=4 super-Yang mills, you see new symmetries becoming manifest that were not there at the naked eye when you were doing Feynman diagrams. Then, in physics, whenever you have simplicity, and moreover, you discover new symmetries that were not there, you start to think that you are onto something and say, well, maybe this is the right formulation for the theory. Okay? Very good. But before we learn how to run, I guess we have to learn how to walk first. So let's start with discussing the object of study, which is the S matrix. Okay? So we all know very well that our friends, the experimentalists, they prepare a state, okay, which I'm going to denote by, they prepare a state that I'm going to denote by psi plus, which is called the in state. And then they measure a state which is called the out state. And if you compute the overlap of the two states, you get the probability amplitude, okay? And this set of probability amplitudes is what's called the S matrix. Now, in practice, it's hard to deal with these objects, so we usually find a representation with free particle states and an operator called the S matrix operator. Okay? Now, what's nice about free particle states is that free particle states, okay, these are free particle states, are the tensor product of one particle states. Of course, they are free, so they don't interact. So if you have n particles, you just describe it as a tensor product of n one particle states. And what is nice about one particle states? Well, what's nice is that they have to be classified by irreducible representations of Poincaré. Okay? So in this school, you have seen many derivations of representations of the of irreducible representations of Poincaré and super Poincaré. Okay, let me denote by lambda and a Lorentz transformation and a translation. But today, we're going to mainly concentrate, or only concentrate, on massless particles. Okay? That might be something that you... This is something that might have shocked people in the 60s when they were exactly studying the S matrix as a program. They thought that studying the S matrix was the correct thing to do. And at the time, massless particles were not very well received. In fact, they thought that massless particles were not nice objects. And as we will see today, it's precisely for massless particles that if they had tried their program, everything would have worked beautifully. Okay? So, well, the interesting thing is that at the same time, Penrose was thinking about massless particles as being the fundamental object. So it's quite interesting. I don't know the story very well, but it would be interesting to figure out why one crowd of people didn't talk to the other crowd and just made spectacular progress. So we're going to be dealing with massless states, okay? And they are, the one particle states are, of course, classified by their momentum and helicity, okay? As you all know, under Lorentz, okay, So I hope you all know that under Lorentz transformations, these one particle states transform as follows. Okay? They pick up a phase, because in this case, the little group is a group of transformations of motions in the plane. Okay? And we only pick up representations that transform under the rotation part of the little group. Okay? Now, very good. But what do we really call amplitudes? Well, we are not interested in the S matrix by itself, but only in the interesting part of the S matrix. Okay? So we remove the part of the S matrix that is given by nothing happening, and we're going to concentrate on this piece. Okay? That's what we're going to call the amplitude. Now, the amplitude usually in books, the data that you give in order to define the scattering amplitude or the particles that you're going to scatter is given by the momentum of the particle and an object which is a little bit ugly, which is called the polarization vector if you're dealing with particles with a spin 1, or a tensor if you're dealing with particles with spin 2. Okay? And these polarization vectors, they are supposed to do a very dirty job. The dirty job that they are supposed to do is to ensure that whatever you construct transforms correctly under a Lorentz transformation. So these vectors are supposed to do very, very ugly things. And that is part of the complication of Feynman diagrams. Okay? Now, how can we get rid of this? Well, we just have to find the right variables to study the object. There is a set of magic variables that I'm going to advocate today, but then tomorrow I'm going to say, no, those are not the good variables, really. We're going to introduce even better variables. But imagine that I didn't say what I just said, okay? And let's get excited about these variables. That's not a very good technique, right? To be pedagogical, but it's just so that you will come tomorrow and you will be excited. So the first observation is the following. We know we're dealing with massless particles, right? So we have to impose, if you have a 4 vector, a generic 4 vector, its norm square is not 0. So saying that for each particle that you are scattering from 1 to n, pi squared is equal to 0 is a constraint, a very ugly constraint. You have p0 squared minus the p vector squared equal to 0. That's a nonlinear constraint. Okay? So we want to find variables that trivialize this. Okay? So that given the variables for every particle, we don't even have to think that they are massless particles. Okay? Well, how to do that? Well, it's not that hard. Of course, nothing is hard once you know the answer. But, well, let's just contract the 4 vector with the Pauli matrices, okay? Including the identity so that you have a 4 vector. Now, this object is a 2 by 2 matrix, okay, whose determinant happens to be the norm of the vector. Now we have that these vectors have 0 determinant, okay, these matrices, and that means that they are of rank 1. And therefore, they can be written as a tensor product of 2 vectors. Okay? People usually like to denote them by lambda and lambda tilde. Okay? But lambda and lambda tilde are nothing but vectors in C2. Okay? They are just points in C2, just complex vectors. Now, of course, real particles, physical particles, will have P real vector, and that would be a constraint on the lambda lambda tilde. It would mean that lambda A bar, or the complex conjugate, must be equal to lambda tilde A plus or minus, where plus or minus tells you if the vector is future directed or past directed. Okay? Now, but you see, we have succeeded. Just give me two vectors, any two vectors in C2. These are called spinors because they transform as spinors under the Lorentz group. Know that the Lorentz group acts as SL to C in this space. Okay? So give me any 2 points in C2, and I can construct for you a massless vector. I don't have to impose any constraints. So that sounds great. But you would say, well, there surely has to be a price that you have to pay, right? Because that looks very, very trivial. So naively, the price that you have to pay is that this relation is not invertible. Can everyone see why it's not invertible? Well, clearly, if somebody gives you a pair of lambdas and lambda tildes, and somebody else gives you another pair of lambdas and lambda tildes, which differ by a rescaling of this form, you get the same momentum. Okay? So the price to pay is that you introduce a redundancy. Okay? Now, for real vectors, this redundancy is nothing but a U1 because T is constrained to be a phase. Well, but is there any other phase around in this blackboard? Yeah, somewhere here, right? Somewhere hidden here. That means that this is great. This is actually great. Because all the ugliness of the polarization vectors can be completely gone if we do the following. If we declare that under a Lorentz transformation, we define the lambda of our particle to be to transform as a one-particle state of helicity half, okay, where this is the usual action on the spinors, then we're in business because any function where we can get rid of this lambda here, this capital lambda, which is the Lorentz transformation acting on this, and which has the correct scaling of lambdas and lambda tildes so that we get the correct transformation as one-particle states, that would be something that has the right or it has a chance of being an S matrix, and it transforms correctly under the Lorentz group. Very good. So how do we get rid of this lambda here? Well, we have to make invariant inner products of these vectors. But how do we do that? Imagine that you have a spinor I and a spinor J. How do we make a Lorentz invariant inner product? Well, we contract with AB with the antisymmetric tensor. Okay? And this is usually denoted. Some people like to put a comma. Of course, I won't write the comma. I'll forget the comma many, many times. And the same thing can be done for the spinors of the opposite chirality. And this is denoted by I and J. Okay. Very, very good. Any questions? Yes.
Could you repeat the reasoning why this? I mean, okay, so T rescaling does not change the momentum.
Yeah.
And I kind of missed how that feeds into the Lorentz transformation.
What I'm going to do is to use that redundancy that we have here in order to construct something that will transform correctly under Lorentz transformations, right? So I can do that if under a Lorentz transformation, I define the lambdas and lambda tildes that enter in the definition of my P to be this, and I build a function that has the correct transformations or scaling properties so that it will pick up a factor like this for each particle state, for each one particle state, okay? So I need the S matrix to pick up this factor under a Lorentz transformation. We will see precisely how that is done, okay? But before we do that, we have to do, let's see. Okay. Where is the, yeah, here they are. Oh, yes. Did I what? The polarization. The polarization. Oh, very good. Yeah, yeah. So now, excellent. That's a very good question. So what do we get from here? Well, we get from here that our scattering amplitude is just determined as a function of lambda A for each particle and 1 lambda tilde for each particle and the helicity of the particle. We have gotten rid of polarization vectors. Forget about polarization vectors. They are not there anymore. Okay? We will just see how to construct functions that transform correctly under the little group transformation. Okay? But I said that before we do that, let's see what happens under a Poincare transformation, which is just a translation. So we know that on the one particle states, this is supposed to take a state P and send it to e to the P dot A, where A is a vector that we are translating by, okay? And the invariance of the S matrix of the amplitude means that if we have our amplitude and we applied a Lorentz transformation on the one particle states, that should be equal to this. Okay? We're applying the same transformation to every state. From each state, we pick up this phase factor. And the invariance of the S matrix tells us that this must be true. Okay, with an I here. So how can this possibly be true for any A? Okay, the only way this can be true for any A is if our function M is not really a function. The only way we can satisfy this is if our M is actually a distribution that has support on the sum of the momenta of the particles. Okay? And this is what we call momentum conservation. Okay, very good. So now we have everything we need to see the power of these new variables. Okay? We're going to compute what might seem as an academic exercise, but it's going to be very, very important, trust me. So we're going to compute 0 in a very interesting way. So we're ready to see the power of these new variables. We're going to compute a 3-particle scattering amplitude. Okay? Well, probably you all know, right, that when you scatter 3 particles, 3 massless particles, you probably all know what the answer has to be, right? I just gave you a hint. 0, right? So we're supposed to compute 0. Okay, let's see. Well, let's try to see why we say that this is 0. Well, this is our scattering amplitude. Okay? Each particle with its corresponding helicity. Of course, each particle comes with its own lambda and lambda tilde. Okay? Now, momentum conservation tells us that P1 plus P2 plus P3 is equal to 0. Okay? So from here, we can see something interesting. If we move P3 to the other side and we square this vector, what do we get? Let's square this. So we find that P1 dot P2 is equal to 0. Well, we can do that for every one and conclude that P2 dot P3 is equal to 0 and that P3 dot P1 is equal to 0. So you would say, well, we don't have any kinematic invariant to construct the amplitude, so it better be 0. That's very good. But here is an exercise for you. Show that the inner product of 2 massless vectors, when written in the spinor helicity formalism, is equal to the only thing it can be, that is Lorentz invariant, the inner product of the corresponding spinors. Okay? Now you see that this is quite remarkable. This thing here is just a quadratic constraint that is the sum of squares, right, with a minus sign somewhere. But in the new variables, this object has factored into 2 pieces. That's quite remarkable. Okay? So we have somehow linearized the problem. This is a quadratic constraint, and it has become reducible. It has become the product of 2 factors. Now, these statements here are the statements that 1, 2 is equal to 0, 2, 3 is equal to 0, 3, 1 is equal to 0. Okay? Well, now you see that naively we could say, well, we can solve these equations and not set every kinematic invariant to 0, because we could set all the brackets, angular brackets, to 0, and don't do anything to the square brackets. Is that possible? Look at that board. Can I say that? Can I just set to 0 the angular brackets and not the square brackets? Sorry? Very good, very good. So if one of them is 0, the other one must be 0, right? So great. So we conclude that for real momenta, really there is nothing to do but to declare that this is 0. Okay? Well, but how about let's play a little game, okay? And let's complexify momenta. Okay? We will allow, just for the sake of this lecture, the PIs, all the momenta, to be complex vectors now. Now, if they are complex vectors, lambda and lambda tilde are independent. In fact, the Lorentz group becomes the direct product of 2 copies of SL to C, each of which acting on the lambdas and lambda tildes independently. Well, that sounds good. Why it sounds good? Because then we can definitely solve these equations by setting only these ones to 0 or these ones to 0. Okay. But before we continue, let's see how we can satisfy momentum conservation. Say, when we solve imagine we're looking at this solution, right? So now the two brackets are independent. So we can set this to 0 and keep the other ones non-zero. Let's see how we can solve momentum conservation. So if you have two vectors whose antisymmetric tensor product is 0, that means that the two vectors are proportional to each other, right? So remember that these lambdas are vectors in C2. So this being 0 means that vector 1 and vector 2, or spinor 1 and spinor 2, are proportional to each other. Now, 2, 3 being 0 means that the second and the third are also proportional to each other, and therefore we find that this must also be true. So this is, or this implies, that every lambda I is some proportionality constant with some universal spinor, or some universal vector in C2, zeta. Now, let's use this in momentum conservation. Now, momentum conservation written in terms of the lambdas and lambda tildes becomes this equation. Okay? Let's use this constraint. So we write this as we can pull out the universal spinor zeta. And we conclude that for momentum conservation to be true, we need this to be 0. Okay? So from here, we can find the alphas. This is always possible because this is a constraint. This is saying that three vectors in C2 are linearly dependent. But that's, of course, true. So the solution is that the alpha i's are given by this. And when you plug that in here, you find an identity that is called Schauten's identity. Okay? This is what Pedro was talking about in his lecture. And I think he got a sign wrong, but when he was doing it, but he told us that he might have gotten a sign wrong, so that's fine. Now, if you take this and you contract it with any spinor that you like, say spinor L, okay, you find the following. So you get these brackets here, and you contract with a spinor L. So you find Ij, Kl, Ki, Jl, Jk, Il equal to 0. And this is what people recognize as Schauten's identity. But it's nothing but the statement that three vectors in C2 are linearly dependent. OK, great. So now we can go back to our three-particle amplitude. Yes?
Why do you not have two of these things, 0 and 1 of the square brackets?
Oh, great question. Yes, yes. So if you have two of them equal to 0, means that spinor 1 is proportional to spinor 2, and spinor 2 is proportional to spinor 3, right? But in 2 dimensions, that implies that the spinor 3 is also proportional to spinor 1. So the third one is automatically satisfied. OK. Great. So that means that our three-particle amplitude can be non-zero as long as we choose either one solution or the other solution. Okay? So that's the most general three-particle amplitude. A function that depends only on the angular brackets, plus a function that only depends on the square brackets. But Lorentz implies okay, meaning the little group transformation tells us that if we rescale each particle independently by a different scaling factor, which now doesn't have to be really a phase, right? Because these guys are completely independent, we should pick up this factor in front. That means that these functions are supposed to be homogeneous of some degree under the rescaling of lambdas and lambda tildes. And the degree is controlled by the helicity of the particle. Now you can immediately see the power of the whole construction, right? Because you see, there is no way you can make something out of just the angular brackets that is invariant under this rescaling, right? So if you only have the three angular brackets, I encourage you to try to construct a rational function out of that that is invariant under that rescaling. Well, it's easy to convince yourself that it's impossible, and that means that under this rescaling, just imposing this condition will completely determine these functions, okay? So let me give you an example. Or I encourage you to try the following. Assume that f and g are generic functions, okay? And expand them in Taylor series or in a Laurent series in the variables. And impose that these conditions hold, and you will see that you pick up only one term. So let me give you an example. Okay, two particles with -2 helicity, helicity -2, and the third particle with helicity 2. Okay. Well, I claim that for f there is only one solution, and the solution is the following. And for g there is also one solution, which is unique. Okay? That's it. That's all what this amplitude can be. And note that I haven't mentioned anything about perturbation theory, 3-level, 1-loop. No, this is all this function can be. It cannot be anything else. But remember what we said about scattering amplitudes for real momenta, 3-particle amplitudes. What are they supposed to do? They are supposed to vanish when we use real momenta. Is that true of that function? In other words, if you take both kind of brackets to 0, what happens to that function? Well, this one goes to 0. What happens to the other one? It blows up. So that solution is not physical. So what do we have to do? We have to declare that kappa prime or kappa tilde is 0. Okay? So this piece is not there, and we have definitely computed our first amplitude. Completely unique. Now, there is something very, very strange, you might say. Imagine that we didn't do 2, but this was an S. Okay? Well, it's easy to write down the answer. It's just S here. Do you see anything strange about this formula when S is odd? Well, if S is odd, there is something very odd about this amplitude. What is strange about the amplitude? Well, that it becomes antisymmetric under the exchange of 1 and 2. That's very weird. That's not physical, right? So who tells me which one comes first and which one comes next? Okay? So we just conclude from here that if we have all the spins, this object must also be 0. So if we declare we have Ks for the spin, we conclude that this is 0. Well, but you would immediately complain and say, wait a minute, but if m is equal to 0, this is spin 1, and we know that we have a scattering of Yang-Mills particles, right? Gluons scatter. Very good. But remember that here, I've assumed that I have only one species of particles. I only have one kind of particles. And we know that photons don't interact. So this is consistent. Okay? Not only that, but it tells you that any particle with odd spins will have 0 scattering amplitude. All right. Any questions? Yeah. That's a very good question. You see, the spin or helicity formalism that I described seems to be very, very tied up with 4 dimensions. So in higher dimensions, you also have what are called pure spinors and other kind of variables, and people are investigating if there are nice ways of doing it. People have succeeded in 6 dimensions, and presumably you can succeed as well very nicely in 10 dimensions. Sorry? Oh, if the spin is 0. No.
You said that you deduce that for a spin the amplitude vanishes, but for real moment they vanish anyway.
No, what I said is that for any spin, we should declare kappa tilde to be 0. And I said that for m equal to 0, meaning, sorry, and what I said is that for S odd, we should declare that kappa S, that depends on the spin, also vanishes. That's what I said. Is that clear?
Yeah, but for real momenta anyway vanish.
For real, yeah, sure. So I have to apologize. So we have wasted like 40 minutes computing 0. Yeah, that's true. Yeah, but I told you to trust me that this will become useful. Now, this is a school about supersymmetry, right? So we haven't done anything about supersymmetry here. So, yeah, sorry. What happens if?
You have a set of U1 that should vanish into
We will see. Don't worry, that will be a nice exercise for you in a few minutes. Yes?
This also happens for n larger 3.
Sorry, can you speak up a little bit?
Yes. For n equal 3, you can write in terms of 2 functions.
Oh, for 4 and higher.
Can you write?
No, you see? Very good, very good. Yeah. So imagine you have n equals 4, right? Now, if you have n equals 4, if you have n equals 4, what I did there will not work, right? So you will not have precisely that factorization of the solution. The constraint of momentum conservation will not factorize like that. All you can conclude is that P1 plus P2 squared is equal to P3 plus P4 squared, right? So there is nothing that you can tell. So this trick will not work for the 4-particle amplitude. 5, no. 6, no. Sorry, it's just 3 particles, and it turns out to be 0. That's life. Okay, so now we're going to do supersymmetry. So if you thought we were wasting our time computing 0, now we will compute 0 supersymmetrically. Okay? And since I want to be very high up in the phase diagram that you drew over there, we're just going to be dealing with maximally supersymmetric theories. Okay? So the amount of supersymmetry is going to be equal to 4s, where s is equal to 1 for super Yang-Mills and 2 for supergravity.
When you talk about one amplitude, I mean, if you have like color getting through both.
Yeah. We're very good, very good. Yeah, very good. So the precisely, yeah, let's say it. Imagine that you have different species of particles, right? So we now have to give the label of the species. Well, how can we solve the problem of this thing being weird and antisymmetric? Well, we now know that the coupling should depend on the species of the particles, right? So which particles you are scattering might have different couplings. They don't have to be all the same. So you can allow this particle to be, the coupling to be something that depends on the 3 guys, right? But if we want to cure this problem, this coupling better be proportional to something that is antisymmetric in the indices. Okay? So we learned that at least you need 3 particles, 3 species. For 2, you can't do it. 1, you can't do it. For 3, there is a chance. Yeah, it's still 0. Yes, I agree. Sorry? Yeah. That's sad. Yes, it's true. Definitely true. Yes. Sorry?
For scalars, you put ks equals 0. S equals 0.
Oh, if you put here s equal to 0, well, it's just a constant. It's just a 3-point amplitude of the 3-point function of safe lambda phi cube.
No, but we saw that, we noticed that for real movement it should vanish. It doesn't vanish. It's a constant.
Well, scalar particles, being massless or not being massless, is really not a very. There is nothing special for a scalar particle to say that the particle is massless or massive, right? So let's move on. Well, we have SUSY, we have supercharges, and by now you're very familiar with them. And just to confuse you, I'm sure I'm going to use completely different notations. But you should be happy with that. Doesn't matter. So this index I is the R symmetry index. Okay? Which is an SUN index. Now we know, probably John Bagger told you how to construct supermultiplets by acting with a supercharge on, say, a vacuum that is a one-particle state with, say, with helicity minus s, okay? And and declare that this is a vacuum, so you get 0, or that this Q bar annihilates this, okay? If we had Q, we will have to start with something that has plus helicity s, okay? These are the highest weight. Now we can start applying, to construct the full supermultiplet, we can start applying the opposite supercharge. So let's write all the indices. So here is your second exercise. Which is build the full n equals 4 and n equals 8 supermultiplet. Okay. Count the states. So this is probably something, well, if you haven't done it, just do it. That's good. Now, but we want to find a way of thinking about scattering amplitudes without having to split them into pieces and study each 3-particle amplitude. I know it's 0, but we don't want to compute 0 in many, many different ways every time we have to do it for different configurations of particles. If we have supersymmetry, and we have the maximal amount of supersymmetry, the supercharges are connecting the whole supermultiplet together. So it would be nice if we could find a way of talking about a superparticle or a superstate and never talk again about helicity, particular helicity particles. Say the gluon with helicity -1 scattering a gaugino with helicity +½ We don't want to do that. We want to talk about everything at once. Okay? And the trick is to describe it, a one-particle state, as a coherent state. So we define this coherent state. Note that I'm replacing the helicity index that I had before in labeling the one-particle states with now a Grassmann with a set of Grassmann variables, okay, n of them, and this is defined as a coherent state as the action of Q bar on the plus helicity state, on the maximal helicity state. Okay? Now, this is just another spinor or a vector in C2, which is defined to normalize, or is defined to be normalized in such a way that when dotted with lambda of the one-particle state, you get exactly 1. Okay? Now, you could also construct, using Q, you could also construct coherent states now labeled by another Grassmann variable, or a set of Grassmann variables, which we usually denote by eta. Okay? This one is eta tilde, and this one will be constructed using another one, which is independent. It's called eta here. But the nice thing is that we can use any of the two representations we like. We don't have to commit with one or the other. And the reason is that they are related by a Grassmann Fourier transform. Okay? So you can work with any representation, the eta tilde representations or the eta representation, and everything should be fine. Okay? Now here is your third exercise. Show that the eta tilde state, or the eta tilde superstate, is an eigenstate of the supercharged Q. Okay? Now, why is this nice? Well, this should ring a bell, right? Remember, if we have one particle states labeled by momentum, when you apply the momentum operator, what happens to them? Here it is. You see how coordinated all the blackboards are, and I mean, this is incredible, huh? Yeah, I was about to raise it. Oh. I have it all here. Use Blackboard to the left, third Blackboard. Yeah. Okay, very good. So this acts precisely like the momentum and picking up the component of the momentum. So as we know, supercharges can induce translations in superspace. So this implies that under a Q-SUSY transformation, okay, a finite one, just like we did for the momentum there, the one particle state must transform as follows. Okay? Now, the SUSY invariance of the S matrix will imply something just like here. Okay, so what do we get? So SUSY invariance tells us that our scattering amplitude must be invariant, means that we should get the same thing okay? Exactly the same, in the same way that we did for momentum conservation, and we can derive the same conclusion. This is only possible if this is possible only if and only if our superamplitude has a fermionic delta function that sets the factor in the numerator to 0. Okay? So we conclude that our amplitudes are distributions supported on momentum, on set of momenta satisfying momentum conservation, and eta tildes and lambdas satisfying super momentum conservation. You can think about that. I think I've denoted this by alpha, where alpha is 1 to 2. These are the components of this. Okay. So we are now ready to go back to the 3-particle amplitude and compute 0 supersymmetrically. So here is our 3-particle amplitude there. Now we want to write down something that is completely symmetric, because remember, now we don't have helicity, right? All the helicity has been encoded into this Grassmann variable. Maybe I should, write that here. I will suppress the momentum conserving delta function, but we all know that it's there. So I'm only going to write the supersymmetric one. Okay. Now, this is our solution for F, okay? But you see, now I have to write a function that contains information of every possible scattering amplitude. So if I had started here, so this formula clearly reproduces this scattering amplitude if we project to some particular helicity component. But I told you that the virtue of doing everything supersymmetrical is that everything should be contained in the same scattering amplitude. Now, if we flip the helicities here, okay, if we put plus, plus, and minus, we should now get something with the square brackets in here, not with the angular brackets, okay? And that formula will not be reproduced by the supersymmetric version. So we have to add another piece in order to reproduce the other part, and this one will vanish in that case. The other piece we have to add is something that looks identical to this one, because indeed we want to reproduce the analog of this formula when the helicities are flipped, but now with the square brackets. But this is funny. We have something in the eta representation and something in the eta tilde representation. But I told you the way to go from one to the other. So if we want to write something that is only in the eta tilde representation, all we have to do is to flip this guy into the eta tilde representation by Fourier transforming okay? So this is a most spectacular supersymmetric way of writing 0. Once again. Okay, very good. Now, another exercise for you is to show that if you rescale if you perform a little group transformation, okay, for a given I, you will find that this function transforms as follows. And for that, you have to use that m is equal to 4s. Okay? Very good. So another exercise is to show that if we now rescale all the eta tildes, okay, by a factor t, okay, so we're going to be probing the R charge of each of these objects. So I want you to show that if you do that, then our 3-particle amplitude here, which is written in terms of 2 pieces, has one piece that transforms as t to the 4s squared, and the other piece transforms as t to the 4s to the first power. Okay? Now the power here is what we call the k charge of the corresponding amplitude. So we can write this formula, this M3, quite nicely as a blob with k equals 2, and as another blob with k equals 1. Okay? And scattering amplitudes will be classified, or we can split them according to their k charge. Okay? Okay, now in order to make even more acute the problem we had here, know that fully supersymmetrically, if the spin is odd, now this object is fully antisymmetric in all three particles. Okay? It's even worse than in the non-supersymmetric version, where it was only antisymmetric in 1 and 2. But still, the same cure, the same medicine will cure the problem by allowing different species and the F and the couplings being completely antisymmetric in the three species under the exchange of the labels. Okay? So for a spin odd, we will also think about this as stress with some coupling constant that depends on them and is fully antisymmetric. Okay, very good. So we are now ready, or almost ready, to compute the scattering amplitudes which are not zero. Yes?
Can you explain why you need maximal supersymmetry?
I don't need maximal supersymmetry, but this school is about supersymmetry, so I better do maximal. No. What is good about maximal supersymmetry? If I had less supersymmetry, right? Say n equals 2 or n equals 1, you see, I could combine still particles into a super state, right? But I still will have, say, the minus helicity, the helicity minus 2 graviton will be together with, say, the gravitino, right? With the minus 3/2 helicity gravitino, there will be one superstate. But then the plus 2 will be together with the gravitino with a 3/2 gravitino state into one guy. But now I have two different guys. I should label one as, say, the plus n equals 1 supermultiplet and the minus n equals 1 supermultiplet. And now scattering amplitudes will still be labeled by minus, minus, plus, plus, minus. So you will have to give me a list of all the amplitudes in order to describe the problem, okay? In order to specify the theory, you'll have to give me a whole list. While for maximal SUSY is enough to connect the lowest helicity to the highest helicity, all into a single object, okay? And here is the answer. I just had to give you one function, and I'm done, okay? Yeah, so hopefully we will see that this will allow very remarkable properties at loop level. At loop level, when you have to sum over the full supermultiplet running in the loop, if you have a symmetry that connects all the states together, something that happens remarkable for say, the minus s helicity particle can be inherited for everybody else, because SUSY allows you to do that. In non-supersymmetric theories, we find that there are remarkable things that happen for the minus s helicity particle, but there is no way to push that property all the way to the other states. And therefore, when you have the other states, they spoil the miraculous properties. Okay? That's what's going to be good about supersymmetry, a maximal supersymmetry. Okay? But that was a very good question. For us at the moment, it's just the fact that we can write everything in terms of a single function. Yes?
What is the physical meaning of the K charge?
Sorry?
What is the physical meaning of the K charge?
Oh, well, this is just the arc charge that you define when you just rescale the Grassmann variables. Well, No, this is just a way of, this is just a way of classifying the scattering amplitudes. So we have a fully supersymmetric amplitude. Now there will be different sectors classified by the K charge. Now different sectors will vanish depending on the particular helicity of the particles that you are computing. If you want to compute a particular amplitude with, say, 2 negative helicity particles and the rest plus, okay? Only the K equals 2 sector will have the eta structure to give something non-zero. All the rest will vanish, okay? Okay, so we're just one step from computing something non-zero. Okay, remember that schematically, we are computing this part, the non-trivial part of the amplitude of the S matrix. And now we have unitarity, right? Unitarity tells you that S dagger must be the identity. But in terms of M, if we put the I appropriately and the delta functions, this is a formula we write in every book. That this must be equal to okay. Now this formula, just as written like this, doesn't look like something that can give us a lot of information. But if we represent it diagrammatically, it's going to be very, very interesting. Because basically here it tells us that the singularity structure of the function M is completely determined by what kind of intermediate processes can happen in the problem. See that you have 2 scattering amplitudes, and we sum over the intermediate states, and these intermediate states are the on-shell states. So each of these M's are actual scattering amplitudes. So we can represent this schematically by saying that this has to be equal to all the ways the states gamma can go to the states alpha by exchanging one particle that is on shell. Okay? That's one possibility. Another possibility that we have to sum over is a contribution when all the particles in the initial state gamma can go to the particles in the state alpha by exchanging 2 on-shell particles. These lines denote on-shell, okay? And so on. Okay? Now, I would like to point out that this is not an expansion like in perturbation theory, where we span at tree level, loop level, and so on. This is a completely different expansion. Because here I'm supposed to put in the full amplitude. What we mean by tree level, one loop, and everything. This is really a different kind of expansion. But it tells us something very, very interesting. So you see, here we can think about this as if in the imaginary part, say we're considering a scalar field theory of this M. And on this side, just looking at this piece, we conclude that the imaginary part of M must have something that produces something that looks like a delta function. This particle must be on shell. So this contribution looks like a delta function of all the momenta going into all the momenta gamma coming here. Momentum conservation tells me that the momentum of this particle, of this intermediate particle, is the sum of the momenta of all the incoming particles. And that contribution will only play a role when that sum squared is equal to 0, is on shell. Okay? So this piece leads to something like this. And now I have to find out a function m whose imaginary part can produce something like this. Okay? Have you ever seen something whose imaginary part can give a delta function? Well, if you take the imaginary part of 1 over p gamma squared plus I epsilon in the limit when epsilon goes to 0, that happens to be delta of p squared. Okay? So this is telling us that the poles of the function m can only be of this form. If we had any other pole, we would see it, right, in this unitarity relation. So we conclude that the only poles the matrix, the function m can have are poles of this form. Okay? And not only that, we also know the residues of the poles. What are the residues of the poles? Well, you compute the residue by going very, very close to the pole. So you're very, very close to where there is a delta function. And this tells you that the residue must be the product of two on-shell scattering amplitudes. And that's what's called factorization. Okay. Okay, so in the last 10 minutes of today's lecture, let's do perturbation theory. But not in the way you are used to. So in field theory, we say that the leading order is called the three-level approximation. Okay? But I haven't talked to you about Feynman diagrams or Lagrangians or anything like that. So talking about three-level doesn't mean anything to you, or it shouldn't mean anything to you. Okay? So I don't want to talk about that here. I would like to propose a new name for what we're going to do. We're going to do the approximation in the, we're going to call the rational function approximation. And why do I know that this is an approximation? Well, because unitarity tells me that this singularity must be there. And this singularity is related to a branch cut. So it tells me that M also has branch cuts. Okay? The first term tells me that the M has poles. The second one tells me that M has branch cuts. But say, well, I don't want to compute branch cuts. So let me start and pretend that the function is a rational function. Okay? So I'll assume that M is a rational function. Okay? So that's going to be my approximation. Of course, we know that, literally speaking, this is not true because we have, this is a distribution. So it's not quite a rational function, because this is not a rational function. But whatever multiplies that is a rational function in our approximation. So this M hat is what I'm going to assume is a rational function. Okay, very good. Now, if you have a rational function and you want to, and you have some knowledge of the singularity structure, meaning the location of the poles, the pole structure, and the residues, how do you go and compute it? Well, we claim we have a control on the poles and the residues. So we should be able to compute the scattering amplitude. Okay? Imagine you have a function f of w that is a rational function, so it's just a ratio of two polynomials, p and q. Well, how can you determine this if you know the location of the poles and the residues? Well, a trick would be the following. You just take the rational function, deform the variable by a z variable, and integrate, perform this contour integral. That's all you have to do. Now, in the z plane, if we choose a contour where z is very, very close to 0, meaning it's a very small circle here around 0, this is an identity, right? It's just a trivial identity. But if we deform the contour, we will now pick up all the singularities of the function f, which are being probed by the deformation. Okay? So we can also write this function as a sum over the contributions of all these residues. But these residues are just the poles and the residues evaluated and the residues associated to those poles. So if we have a control on those poles, we can reconstruct the function in that way. But we have to be careful here. M only makes sense on the support of the delta functions, okay? So whatever deformation we're going to make, it better be a deformation that keeps M on the support of the delta functions, okay? So that's what we're going to do. And we will end with that. Okay? So we need a deformation. We're going to deform our variables, which are the lambdas and lambda tildes and etas. But we need something that will perform a deformation of these guys, but keeping us on the support of the delta functions. Okay? So I invite you to try and find deformations that do this, or classify the most general deformations, but I can just give you the simplest one. Okay? The simplest one is the following. Say you take two particular guys, particles 1 and 2, so your exercise is to show that if you deform this, momentum conservation is preserved. So it satisfies the first condition. But now you see that we also have to do something to etas in order to satisfy the second condition. And what you have to do is only to deform eta 2 of z and make it this. Okay? So this deformation should work. Okay? Now, I'll just end by saying that, okay, fine, so we have defined our function m as a function of z. So this is the analog of this function here. We can perform this integral and evaluate everything at the poles. We know what the poles are. These are the poles. And we know the residues. Now there is something very interesting. You see, these poles, for generic momenta, real momenta, external momenta, these poles are going to be located at complex values. So these scattering amplitudes entering in the residue are not going to be completely physical amplitudes. Well, it depends on your taste. If you don't care about reality, they are completely physical because they are on shell and they satisfy momentum conservation. But there is a catch. The catch is that the momenta incoming there are complex now. Okay? So we're going to be able to build physical scattering amplitudes with external particles, which are all real, very beautiful, happy, and they are all nice, in terms of scattering amplitudes with less particles, but now evaluated at complex momenta. But we know what happens when we have complex momenta. The 3-particle amplitudes don't vanish. Okay? So all the effort that we put in the first lecture in defining the 3-particle amplitudes is going to pay off because we're going to use them as building blocks, because now they are not 0, because we're building these physical amplitudes out of pieces which are evaluated at complex values of the momenta. So the 3-particle amplitudes will enter, and jamming together 2 3-particle amplitudes, we will produce a physical 4-particle amplitude. Putting again another 3-particle amplitude in, we will produce a 5-particle amplitude, and so on. So we'll be able to completely solve or generate the whole 3-level S matrix of these theories by just using together the 3-particle amplitudes all over and over again. So all the effort we did will completely pay off, and the whole S matrix will just be determined, if you think about it, by super Poincare invariance. Because that's all we use in determining the 3-particle amplitudes, which are going to be the building blocks of the whole structure. So in the rational approximation that I am advocating, we have solved completely the theory. Okay? And that's what we're going to continue this afternoon in the discussion session. Okay, thank you.